Hello everyone, welcome to my presentation on channel coding for beyond 5G. I'm going to introduce primitive rateless code and explore different properties of this code and see how they are performing in comparison with the existing codes. So here is the outline of my talk. I first provide a brief introduction and on why channel coding is an important problem for future 5G and next generation 6G. I'll then introduce primitive rateless codes. Then I will discuss how we derive the average Hamming weight distribution of PR codes. Using that, I will derive a bound on the minimum Hamming weight of PR codes and show that there is always a PR code that can meet this bound and show that the bound is really close to the Gilbert-Warshaw bound. I'll then provide show some results and provide some discussion and future research direction. So first, I'll introduce the problem. So the channel code design for the 6G is really important and a challenging problem. So we have seen this figure quite a lot in recent years, and for the next generation, we are going to expand and improve the capabilities of our mobile network many folds in different, directions. For example, we are going to increase the data rate, improve the spectral efficiency, connection density, reliability, for example, from 10-5 to 10-7. So this is mainly to support many applications and services per square kilometers, and also improving the reliability from 10-5 to 10-7. So there are lots of application scenarios that we are going to support in using the 6G. But what remains very challenging is that the reliability and latency requirements are expected to be very diverse. So we have lots of applications with different requirements in terms of data rate, in terms of reliability, latency, and also in terms of the capacity. So some of these requirements, for example, reliability and the data rate, are beyond what the current 5G standards can achieve. So channel coding has been always at the heart of any communication systems, and for the future standards, it also play a key role to meet these stringent requirements and guarantee different level of reliability. So for beyond 5G and also 6G, we require flexibility in terms of the block lengths and the code rate. And also, we need short and moderate block length codes that performs close to optimal in terms of the packet error rate. And the reason that the design has been challenging is that there are new communication scenarios that mandate the design of these codes differently. One of which is the massive multiple antenna scenarios and also the millimeter wave communication that we have different path, and we have almost, when we realize the channel, we actually, at the receiver, we have a non-stationary channel. So most of the design of the channel codes are based on the assumption that the channel is stationary, but in some scenarios, like these massive multiple antennas, we have these non-stationary channels. There have been some recent works that try to optimize these polar codes, this design of polar codes for non-stationary channels. The other interesting scenario is the low capacity scenarios or low SNR scenarios, which is really important for massive machine type communication, and we are going to use low-cost devices that that they want to consume a little amount of energy to send very small packets. So the signal to noise ratio in these scenarios are extremely low, and we are interested to design some codes that can actually perform close to the optimal, I mean here, maximum likelihood performance. So the design of the codes with flexible block lengths and rates and decoding algorithms which are capable of handling non-stationary and low SNR channels with limited or no channel state information is required. So let's have a look at the different codes that are being standardized for the 5G scenarios. I chose this LDPC, 5G LDPC and 5G polar codes. And on the left, you can see the LDPC codes when the block length is 128. So you can see that so these curves shows the normal approximation bound, and you can see that the LDPC code has relatively large gap to this bound. So the polar codes, the standard polar codes, for this I chose the successive cancellation list decoding with list size 32, and so these polar codes are using the 11-bit CRC. So you can see they perform much better than this LDPC code, but there is still a gap to this normal approximation bound. For a slightly larger block length at 512 bits, you can see that the gap to the normal approximation actually reduced for polar codes, but the gap still exists for the LDPC codes. And one other thing is that at very low block error rates, so these LDPC, the standard LDPC code shows some error flow. So for longer block lengths at 1000, close to 1000, these two codes performs relatively close to each other, but we have this problem with the error flows almost for the LDPC codes at really low word error rates. So the important thing that I want to emphasize here that there's still some room for improvement. I mean, in terms of the gap to this normal approximation bound, and so this is really the matter of designing codes and also optimal decoders, because the performance really depends on the decoding and how much complexity you can tolerate. So so to summarize what would be the future of this design of this channel codes and the requirements, we need some codes with a strong error correction capabilities that can really achieve this performance without the overhead of an older CRC codes. This is really important for short packet communication because we cannot accommodate a large amount of the packet to be actually consumed by these CRC bits. So the other thing is the link adaptation. Currently, we use this adaptive modulation and coding, and that requires the feedback from the receiver, and the latency associated with that is quite large. I mean, for the 4G LTE, we have around 5 to 8 millisecond latency that is consumed for this feedback message and this CSI feedback, which actually violates the latency requirements for many URLC application. And also, we need some new techniques that can support these applications that the CSI is not available, or some limited CSI are available at the receiver sites only. So Besides all these, we also need rate compatible codes. So 5G already have this rate matching principle that it's trying to support various requirements and having different code rates and with that different block lengths. So mainly to support this rate matching, we need this rate compatible codes and the general idea of this rate compatible is there a set of codes with the same dimension, and usually the higher rate code is a subset of the lower rate code. So we usually use this puncturing to generate rate compatible codes. That has been done for the polar codes, and I mean in the 5G standards we use this puncturing to generate rate compatible codes. But usually finding the best puncturing pattern is through the computer search. The other approach is the extending, is another approach, and this protograph-based wrapped like LDPC codes in the 5G standards are actually generated by this approach. But usually when we have these extending approaches, especially for short codes, usually we cannot guarantee high minimum Hamming rates, and that's therefore designing the rate compatible codes for short messages that support bit level granularity of code word size and also maintaining a large minimum Hamming rate at various rates is still open and a challenging question. So with all these introduction, I'm now going to focus on the primitive rateless codes and to show that these codes perform very close to the best known codes at short block lengths, and also they demonstrate excellent rateless properties, which means that they have these inherent rateless properties, so they are rate compatible codes, so they could be an excellent candidates for future wireless standards. So the definition of this primitive rateless code is really simple. They are characterized by a primitive polynomial px with the maximum degree k. So this k is the message length or the dimension of the code. And for this px, we assume that this alpha is the primitive element over gf2k, and the generator matrix of the primitive polynomial can be easily constructed by just the binary representation of these powers of these primitive elements. And so I just listed from alpha 0 to alpha n minus 1. So that can be for any n. So we can see that because alpha is primitive element, so this matrix, the rank of this matrix is k, and so this is a valid generator matrix. And also just because of alpha is primitive, so this set is the entire field. So because this alpha is a primitive element, the parity check matrix of the PR codes can be written like this, because we can see that the elements of the code words actually satisfy this somehow this linear recurrence function, which is characterized by the primitive polynomial. So you can see that each row is actually a cyclic shift of this the first row, but we need to take we need to also note that this is not a cyclic code, because this px is a primitive polynomial. So in fact, when n is 2k minus 1, so this the code would be equivalent to a cyclic code. I will later discuss about that. And so Because these codes are represented by this primitive polynomial, we can easily construct them using linear feedback shift registers, because we can easily see that each code word actually satisfies this linear recurrence function, which is characterized by this primitive polynomial, and then we can easily construct the code using this linear feedback shift register. And in fact, the code words can be realized as the subsequences of a maximum length sequence. So, we can easily generate them by using the LFSR. So a more general representation of the PR code is by using a Boolean function. So a Boolean function is the transform from this higher order gallery field to a binary field, and they have this some linear properties that the function over the linear combination of the two elements is the sum of these weighted functions. So we can consider the PR codes as this Boolean projection that any coded symbols is actually, we apply the this function over the this power of alpha, and we can generate as many coded symbols as we want. So to show you an example, I consider k equals 4, and we have this primitive polynomial, and I consider this Boolean function, which is simply the XOR of all those elements. I construct the whole field over this circle. You can see from alpha 0 to alpha 14. And now I want to encode this message, which is 1100, which is equivalent to alpha 6. And I just apply this Boolean function to this message, which is the XOR of all these elements, which gives us 0. Then the next bit is the Boolean function over alpha 7, which gives 1. And we can go through this circle and generate as many bits as we want. We can also go over and over because we can repeat this process. So now I want to show some of the properties of the PR code. When the block length is 2k minus 1, so this PR code is equivalent to the binary Hamming code. And also it is cyclic. So, you know, the binary Hamming code, we have this, the parity check matrix of a binary Hamming code, we list all the possible configurations of the binary vectors of dimension k. And you can see that from the definition of the PR code, this generator matrix, when n is 2k minus 1, is really the parity check matrix of the binary Hamming code. So at any given length n, so the PR code is a dual of a shortened Hamming code, and also any PR code can be realized as a punctured simplex code. So I just want to emphasize that these two properties is not, is not applicable to PR codes only, but any linear block code can be realized as a shortened Hamming code or a punctured simplex code. So this has been shown in this paper. So another interesting thing is that from the definition of the parity check matrix, any PR code is actually the dual of a polynomial code, because we can show that the each code word of the dual of a PR code is a multiple of this primitive polynomial. So a very interesting property of this PR code is that any two PR codes even with different dimension K1 and K2, at any length n, which is larger than the twice of the maximum of K1 and K2, do not have any non-zero code word in common. So as long as the primitive polynomials are different and the length is larger than the twice of the maximum of the code size, then these two code books are distinct and they don't have any non-zero code word in common. So this is very important because we will use this property later to derive a bound for pure codes. And for any message length k, we have this number of primitive polynomials, and every primitive polynomial gives us a distinct PR code. So in fact, we have mk of different PR codes with the same dimension k. So using the first property for when n is larger than 2k, these mk PR codes are all distinct and they don't have any non-zero code word in common. So another property which is also applicable to any code which has the dual code with minimum Hamming distance larger than 3. The average Hamming weight of the PR code is n half, which is the half of the block length, and the variance is n divided by 4. So this is really important when we consider PR codes in the rateless setting, which means that the average Hamming weight of the code increases by 1 as long as we increase the block length by 2. So every 2 new parity bits that we are sending to the receiver, we actually increase the average Hamming weight by 1. So just want to see whether there are some literature, some research that have considered this problem previously or not. So as I discussed, the PR codes can be realized by the LFSR, linear feedback shift register, or in fact, the set of all subsequences of a given length of maximum length sequence actually is equivalent to PR codes. So there have been some work, so here I listed them here, that they try to characterize the distribution of the subsequences of the M sequence. And they mainly try to find the gap between the distribution of the subsequences and the binomial distribution, or something they refer to as the ideal distribution. But their calculation is really complex and cannot be really implemented when k is relatively large. For example, when k is around 20, it's very complex to calculate them. And also, their calculation really depends on which primitive polynomials that we have chosen. So some other works, they try to find some bound on the Hamming weight. And for example, this reference 4 is actually trying to characterize the gap and finding the gap to the this average Hamming weight. And so which really shows that with the block length, the Hamming weight of the subsequences is concentrated around the half of the block length. So finding the Hamming weight distribution of subsequences of M sequences still remains a challenge. So in this work, I'm not really interested in characterizing the Hamming weight distribution of a specific PR code. Instead, I'm interested to characterize the average Hamming weight distribution of the ensemble of PR codes. So we showed that we have mk different PR codes, and here I want to find the average Hamming weight distribution of this ensemble. So if AIX is the Hamming weight distribution of a PR code generated by PI, then if I take the average over all PR codes of dimension K, then I can define this average Hamming weight distribution. In the same way, I can define the average Hamming weight distribution for the duals of PR codes. So this is the average Hamming weight for all ensembles of PR codes, and this is for the duals. So you're all familiar with this Mac-Williams identity, which actually shows the relationship between the Hamming weight distribution and the Hamming weight distribution of the dual code. And because of this linear operation, we can get the same for the average Hamming weight distribution as well. So in the rest, I first try to find the average Hamming weight distribution of the dual codes, and then I use this Mac-Williams identity to find this average Hamming weight distribution of the ensembles of PR codes. So just getting back to the case when we have n equals to 2k minus 1, then the PR code is equivalent to the dual of the Hamming code. So if you're familiar with the literature of these Hamming codes, you may find this formula in those papers. This has been used to characterize the Hamming weight distribution of Hamming codes. So it's really, this formula shows the number of t-nomial multiples with degree up to 2k minus 2 of a primitive polynomial of degree k. So this formula is exact, and so through this, this recursive equation, we can find this number of t-nomial multiples. The interesting property is that usually these t-nomial multiples of a primitive polynomial is distributed almost uniformly across all the possible 2k minus 2 t-nomials of degree at most 2k minus 2. So this is all the possible t-nomial of at most 2k minus 2. And we know that the distribution of this t-nomial multiples is almost uniform. So the probability that a randomly chosen t-nomial of degree at most 2k minus 2 is a multiple of primitive polynomial is given by this, so which is being proved here. The other thing is that when we have a t-nomial multiple, so t-nomial means that the polynomial has a constant term 1. So when we have a t-nomial, then the product of that t-nomial is also a multiple of that primitive polynomial, and this formula is really showing the number of multiples of that t-nomial multiple. So now, if we take the summation over all the multiples of the t-nomial multiples, we can find or characterize or approximate this average Hamming weight distribution of the dual of PR codes, which is mainly given by this nkt. So compared to those previous formulas in the literature that they characterize the Hamming weight distribution of the, for example, the subsequences of M sequence. So this calculation is, relatively easy to find. So in the, next few slides, we can see that we cannot go up to n. We can actually, the summation can be limited to k. So, but anyway, we can easily calculate this, and we can find the average Hamming weight distribution of the dual codes. So let's see how accurate is this. For this figure, I generated all possible PR codes of dimension k, and I found the duals, and then I find the Hamming weight distribution, and then take the average. So the solid lines actually show the exact calculation, and the dashed line shows the approximation that we get here. So you can see that when K and N are relatively large, then the approximation gets very close to the exact result. To better characterize it, I also show the KL divergence between these distributions. Here, I just take one of the PR codes, for example, generated by these primitive polynomials when K is 10 or when K is 19, and showed the Hamming weight distribution of the dual code. So you can see that if the primitive polynomial is selected properly, the average Hamming weight distribution is actually approximating the Hamming distribution of this dual of PR code as well. So which is interesting property, which means that there are some PR codes that their Hamming weight distribution can be well approximated by this average Hamming weight distribution. So now if we use the McWilliams identity, we can find the average Hamming weight distribution of PR codes. And it can be actually characterized by this FNKT. And so this FNKT can be actually calculated using this summation, which only a few terms, which is bounded by the dimension of the code, which is actually really easy to calculate. So the proof of this is available in the paper. So again, I generated the all possible PR codes of a given dimension and compared the exact average Hamming weight distribution with the approximation. You can see that when K and N is relatively large, the approximation is quite accurate. And also we have this KL divergence. We can see that when K and N are large, we can get this really small KL divergence. Again, I generated the Hamming weight distribution when K is 39 at different block lengths. And you can see that this average Hamming weight distribution is actually is very close to what we get from the actual Hamming distribution. So which means that there are PR codes that the Hamming weight distribution are really close to this approximated Hamming weight distribution. So using this Hamming weight and average Hamming weight distribution, now I'm going to define a bound and then prove that there are always some PR codes that can meet this bound. So again, going back to the one of the properties of the PR code, and I just want to restate it here that let's consider that C1 and C2 denote two PR codes that are generated using different primitive polynomials P1 and P2. And we assume that the block length is larger than 2K. Then these codes do not have any non-zero code word in common. So, and the reason is that just as considering the linear feedback shift register presentation of the PR codes, actually all sequences generated by an LFSR with primitive polynomial Px, they all have the same linear complexity K. And when the block length or the length of the subsequence is larger than 2K, then the minimal polynomials of these subsequences is unique. So if these two codes have this, has at least maybe one non-zero code word in common, then the code word should have two minimal polynomials, which is impossible according to this formula, which is has been presented in the very old paper by Messi. So we know that these PR codes, as long as the block length is larger than 2K, they don't have any non-zero likelihood in common. Now, if we use that, we can derive this bound for the PR codes. So this theorem shows that there is at least one PR code with the minimum Hamming weight lower bounded by this D mean, which is really, this D mean is the maximum D, which the sum of the average Hamming weights characterized by the formula that we showed previously, the sum of these average Hamming weights is less than 1. So this D is actually, when we find this D mean, then using this this lemma 1, we can easily show that there is always a PR code that can meet this bound. So now let's have a look at this bound. So this dashed line shows this the bound that we characterized, and I chose 3 different message lengths, 4, 8, and 16, with different polynomials, and I generated their codes at different block lengths and find the minimum Hamming distance. So you can see that for all of these codes, the minimum Hamming weight is actually almost very close to this bound. So the reason that at some points we have this Hamming weight less than this bound is that because maybe at this block length, this primitive polynomial is not the optimal one. So, and also the other reason is that the bound that we showed here, I mean, for the average Hamming weight, is not really accurate when K is very, very small. But a very interesting thing is that the bound that we have here is very close to the Gilbert-Warshamov bound. So the Gilbert-Warshamov bound is just in a simple, definition, is that assuming that the code has a binomial Hamming weight distribution, and then the minimum distance of these codes is actually characterized by this formula. So this bound that we characterize for the PR code is really close to this Gilbert-Warshamov bound. So if we go for larger block lengths, so the interesting thing here is that the bound that we proposed or we found for the PR code is actually identical to this Gilbert-Warshamov bound. So one important thing here is that how to choose the primitive polynomials for PR codes. So this problem is quite similar to the designing these M sequences. And the criteria for the M sequences is that they should be robust to the, for example, some attacks like this correlation attack. So they're usually avoiding having low weight primitive polynomials or very high weight primitive polynomials, because these primitive polynomials with high density usually have low weight multiples. So they usually want to avoid that to have a strong randomness properties. So here I consider 3 primitive polynomials: low density, medium density, and high density. And you can see that the low density polynomials actually have the Hamming weight distribution, which actually diverge from the binomial distribution. But this, or the average Hamming weight distribution that we characterize. But the medium density or the high density actually have a really close distribution to what we characterize using the average Hamming weight distribution. And also it's really close to the binomial distribution. Here I showed the distance to the binomial distribution. You can see that for moderate and high density, the KL divergence is really low, but for low density is relatively high. So using this, I actually generated some good primitive polynomials for PR codes. So the list is actually going up to K40, but I can generate for any block links or any message links. The one good thing is that when K is sufficiently large, for example, larger than 20, a randomly chosen primitive polynomial with almost K half terms actually gives us a good primitive rateless code that can actually generate a code with almost binomial distribution Hamming weight and the minimum Hamming weight close to the Gilbert-Warshaw form. So you can see that this, for example, when K is 10 with these primitive polynomials, the Hamming weights of the codes is really close or even larger than what we get from the Gilbert-Warshaw round. Now I'm going through the result that we have. So based on the average Hamming weight distribution, I can define a union bound. The union bound is actually taking the Hamming weight distribution we characterized here, and also the minimum distance we get from the bound that we discussed. I first compared them with the standard Reed-Muller codes in 5G. So you can see, so this blue lines showing it for the union bound, and the black lines actually showing the result for the PR codes, and the red one showing for the Reed-Muller code. So in most of the cases, the PR code actually performs better. For all of these codes, I'm using the maximum likelihood decoder. So this PR codes performs better, but in some cases it's actually perform worse. And the main reason is that the minimum distance of the Reed-Muller code is slightly better, but we can also search for better codes that may gives us better performance. So one of the reasons that PR codes performs better than Reed-Muller code is that sometimes we have higher minimum Hamming weight. For example, here the PR code has a higher minimum Hamming weight. But in most cases, because of this binomial-like distribution of the PR codes, the number of low-weight code words is much lower than the Reed-Muller code. For example, here, the Reed-Muller code at length 32 has 64 code words of weight 10, but PR code has only 2 code words of weight 9 and 40 code words of weight 10. So the sum of these two is much lower than this that for the PR code, that RM code. And you can see that the based on the union bound, not only the minimum distance is important, but also the number of code words with that weight is also important. So here it shows the comparison between PR codes and BCH codes. So for the BCH code, this is an extended BCH code. You can see at different message lengths close to 6. The PR codes perform close to the BCH codes. PCH code perform slightly better, but you can see that the union bound that we have is actually very accurate, and the PR code perform very close to this union bound. At length K15, again, the performance of PR codes is really close to the BCH codes, and also the union bounds is really accurate. And for longer block lengths, 64 and K equals 24, and even longer, the performance of the codes are really close to each other, and also the union bound is really accurate. And again, the reason that PR code performs very close to the BCH code, even though they have a slightly lower Hamming weight, minimum Hamming weight, is their binomial-like distribution. So you can see that the PR code has really low number of low-weight code words, but the BCH code usually have, even though they have high minimum Hamming weights, but they have relatively high number of code words with that weight. So, I mean, the PR codes, even though they have lower minimum Hamming weight, but because of their low number of low weight code words, they have almost identical performance as BCH codes. So here I'm having a comparison between the standard Polar and LDPC codes. And you can see that for this LDPC code, I'm using the 200 iteration belief propagation. And for the Polar codes, this is the 5G standard with the list size 32. And you can see that if I'm using a reduced complexity order statistic decoding, this PR code actually outperforms these codes. And the other thing is that I want to emphasize here that this red dashed line shows the normal approximation. You can see that the normal approximation is not really accurate at low SNRs and low rates, but this union bound that we have is actually characterizing the packet error rate at low word error rates very accurately, at least for PR codes. So this is showing the performance of PR codes in a rateless manner. So the rateless properties is that we send delta additional symbols as long as we don't receive the acknowledgement from the receiver to decide whether the decoding is successful or not. I'm attaching 2 bits CRC. So to decide when to stop the decoding, you can see that with this realized rate definition, the performance of the PR code is really close to what we get with the bounds that we have with the normal approximation. So I chose normal approximation because at this length is relatively accurate. And also I'm repeating this for the Rayleigh fading channel, and you can see that the performance is really close to the normal approximation bound. So to conclude, I actually introduced PR codes. We characterize the average Hamming weight distribution, and then we derive a bound on the minimum Hamming weight of this code, and we showed that there's always a PR code that can meet this bound as long as the block length is larger than 2K. And this bound is really close and also almost identical to the Gilbert-Warshamov bound. And we showed that these codes perform close to the BCH codes, and also they demonstrate excellent rateless performance. So some future works could be to devise new low complexity decoders for PR codes. The fact that they can be generated by the feedback shift register, then the Breplin-Messi algorithm can be effectively used to design some new decoders. And also finding the optimal primitive polynomials for PR code is also an interesting problem. So that could be another future direction. So so we had this work with Chento, Professor Vucic, and Professor Lee at Center that we had this OSC reviews, reduced complexity OSCs, and so these works can be also used to reduce the complexity of OSD for PR code as well.